A very good evening to all the respected speakers, faculty members, researchers, and participants joining us today. On behalf of the North Cap University and the organizing committee, we warmly welcome you to the day 5 of the ATAL Faculty Development Program.
We sincerely thank you for your continued dedication and enthusiastic participation. Today's sessions are highly significant as they focus on the complete spec to SoC design journey and the rapidly growing influence of AI and machine learning in VLSI and chip design.
My name is Krishika.
And my name is Kashvi.
We are delighted to invite you to be a part of the fifth day of the ATAL Online Faculty Development Program, which continues to bring together experts from academia and industry to share knowledge, experience, and emerging perspectives in semiconductor technologies.
This faculty development program is a pivotal initiative in the context of India's rapidly evolving semiconductor landscape, which is poised to emerge as a global leader in chip design, manufacturing, and innovation. As India's strengthens its semiconductor mission, developing a strong understanding of technologies spanning design to packaging has become essential.
The FDP offers comprehensive exposure to critical areas such as cleanroom technologies, vacuum systems, and semiconductor fabrication processes, including lithography and etching, along with advanced topics like EDA tools, AI and machine learning applications in VLSI, and the complete design flow from RTL to GDS2.
In addition, participants will explore semiconductor packaging, nanomaterials, and analog and mixed signal VLSI design, gaining insights to both foundational and advanced aspects of semiconductor engineering.
Through expert led sessions on global market trends, India's semiconductor assembly and testing ecosystem, and emerging industry developments, combined with interactive discussions and practical insights, this FDP aims to strengthen research capabilities, teaching excellence, and industry collaboration, contributing meaningfully to India's vision of self reliance in semiconductors. It is now our privilege to welcome our first speaker for the day, Ms. Nikita Gulia, joining us from the industry sector.
Ms. Gulia is a senior RTL design and verification engineer at Agnesys Technologies with over 9 years of industry experience. She holds an MTech in VLSI from CDAC Noida and is a recognized expert in system RDL, RTL design, and UVM based verification.
Beyond her core engineering role, she has extensive experience in delivering technical trainings to customers and companies across the globe. Her research contributions also include multiple published papers on register design automation techniques.
With her extensive hands on experience across complex SoC projects, Ms. Gulia brings valuable real world insights into the challenges and best practices of modern chip design.
She will now deliver session 9 titled Spec to SOC, the complete design journey. This session will comprehensively walk us through the transformation of system level specifications into a fully functional system on chip. The chat box will remain open and the Q&A session will be taken at the end. We now invite Ms. Nikita Gulia to kindly begin her session.
Thank you so much for the introduction. Let me share my screen. Can you see my screen?
Yes, ma'am.
Okay, welcome everyone to the session Spec to SoC, the complete design journey. Today we will go over the specification to SoC and in this session. I don't expect that you will understand everything completely, but even if you get a gist of it, it will be very beneficial to you, especially if you look forward to your career in the semiconductor industry. So all the terminologies and all the languages I will be going over is actually in use. and all the processes are actually in use in the industry. So if you're curious, you can go back and then go into more details of it also. So starting with the introduction of system on chip. So, a system on chip is an integrated circuit that combines multiple system components on a single chip instead of having separate chips of processing memory and peripherals on a board. An SoC integrates all of them together. So, why do we need SoCs? The main reason is efficiency. Integrating everything on one chip reduces power consumption, performance improvement happens, and saves space. This is especially important in devices like smartphones, wearables, and embedded systems. An SoC typically consists of several key building blocks. These include processor cores, memory subsystems, communication interfaces, and various physical controllers. All these blocks are connected using an on-chip interconnect. If we compare this with traditional board level systems, earlier designs used multiple chips connected through external buses. That approach consumed more power, required more space, and was slower. So, SoCs solve these problems by integrating everything on a single silicon die. Today, SoCs are used almost everywhere: smartphones, automotive system, network devices, and IoT products. Whenever compact size, low power, and high performance are required, SoCs are the preferred solution. And this slide shows the common components found in an SoC. Not all SoCs have the same blocks, but these are the most common ones. The exact combination depends on the various application. Now, this slide shows a typical SoC design where the C++ program is converted into assembly, and then it goes into the CPU. CPU has its own bunch of registers, and with the help of interconnect fabric, or you can say with the help of a bus, it further communicates with programmable slaves. These are various IPs. IPs in the sense it can be GPIO, input output pins, or it can be a timer to check the clock pulse, count the clock pulse, and they also have bunch of registers under it, having data and address. It can have memory as well, uh, and with the help of a bridge and this another bus. This is the bus AXI. We'll go into more details of this also. And with the help of APP bus, some more slaves are connected here, and these slaves are connected to, say, sensors. And interrupt can also occur at any time, which is going to the this signal is going to the CPU. So this is one SoC, you can say. Now that we understand what an SoC is, the next important question is, where does the SoC design actually begin? So it begins with the specification. A specification is a formal description of what the SoC is expected to do. It is actually written as a document and act as a contract between customers, architects, and design teams. Specifications are critical because every design decision is based on them. If the specification is unclear or incomplete, problems will appear later in RTL verification and integration, where fixing them becomes very expensive. A typical specification describes different types of requirements. These include what functions the SoC must support, how fast it should operate, how much power it can consume, and how much silicon area it can use. So you can think of the specification as the foundation of the entire SoC design journey. A strong foundation leads to a stable design, while a weak specification leads to repeated redesigns. Let's first talk about functional requirements. Functional requirements defines what the SoC should do. They describe the expected behavior and supported feature of the system. For example, a specification may state that the SoC should support certain communication protocols, handle specific data types, or operate in different modes such as normal mode, low power mode, or sleep mode. Functional requirements also define interfaces, how the SoC communicates with the outside world. This includes interfaces to memory, peripherals, and external devices. At this stage, we are not concerned about how the functionality is implemented. We only focus on what functionality is required. And these functionality later guide architectural decisions, RTL implementation, and verification planning. Along with the functionality, specification also defines the performance, power, and area, and commonly known as PPA. I referred to it in the last session also. So the performance requirement, specifically how fast the SoC should operate. This may include clock frequency, throughput, or latency targets. Performance requirements develop heavily on the application. For example, multimedia processing requires high performance than simple control systems. Power requirements are extremely important, especially for battery operated devices. The specification may define maximum power consumption, ideal power limits, or low power operating modes. Area requirements define how much silicon area the SoC can occupy. Area directly impacts cost, so it must be carefully controlled. The key challenge here is that performance, power, and area are interrelated. Improving performance often increases power and area, while reducing power may limit performance. So designers constantly make trade-off based on the specification. These PPA requirements strongly influence architectural choices, RTL design decisions, and verification priorities. Until now, we've discussed specification and RTL at a conceptual level. So now let's look at how specification are actually captured in practice. In modern SoC design, specifications are not just free-form text. They're often written using structured input formats that tools can understand and process. These input formats help describe registers, interfaces, memories, and configuration details in a consistent and machine-readable way. Using structured input format enables automation, reduces manual error, and ensures that same specification can be used across RTL verification software and documentation teams. So input format act as a bridge between specification and implementation. Let's look at some commonly used input format in SoC and IP design. One widely used format is system RDL. System uh, system RDL is used to describe register maps and addressable components in a structured way. It helps ensure consistency between all the teams. Another important format is IP exact. You can get system RDL and IP exact LRMs on Accelera website. IP exact is used to describe IP metadata such as interfaces, memory maps, parameters, and connectivity. It is especially useful for IP integration at the SoC level. In many real projects, specifications are also captured using Excel and Word documents. Excel is often used for register description because it is easy to read and edit, especially for cross-functional team. Word documents are commonly used for high-level functional description. More recently, JSON, XML formats are used because they are structured, flexible, and tool-friendly. These formats are easy to parse and integrate into automated design flow. Each of these formats serves the same purpose, to capture specification in a way that it is clear, reusable, and automation ready. Going into more details of system RDL, So it is used for defining the register and memory. And here I have captured a small code also. So the language goes like this, the keyword reg. So you're defining a register here, and this register has two fields. And from the software side, say from the CPU side or the bus side, this register is read and writable. And from the hardware side, that means on your device there is a pin or a button. From the hardware side, it can the value can only be read, and here the value can be written. Say the name of this field is status, the name of this field is control, and its default value is 1 currently. And this is the name of the register, my register, and it's sitting at the first address as 0 cross 0. So, uh, so this is how multiple thousands and millions of registers and their functionality are being described in a complete system RDL specification. And IP exact, IP metadata description. So, IP exact is an XML-based standard used to describe IP metadata. While System RDL focuses mainly on registers, IP exact describes the entire IP, including registers, interfaces, address map parameters, and connectivity. In the small example shown here, we describe a register named control, its address offset, and its size. The information is written in XML format so that tools can easily parse it. It is very similar to HTML also, which you must be aware of. IP exact is especially useful at the SoC integration level where many IPs and different vendors need to be connected together consistently. So using IP exact helps automating IP integration, reduce manual efforts, and ensure consistency across large SoC design. In simple terms, system RDL is register centric while IP exact is IP centric. Both help bring structure and automation into a SoC design. Similarly, in one input format is Excel, and in Excel also in columns in industry, not everybody is comfortable with the text mode like system RDL and IP exact. So many users would prefer more GUI mode. So they specify information such as register name, address, its field width, access type, preset value in various columns in Excel. And and another one is a Word format as well, which is more human readable, and it acts as a reference for all the teams. So one important concept here is the idea of single source of truth. When specifications are captured using structured input format, the same data can be used to generate multiple outputs. For example, register specification can be used to generate RTL verification model, software headers, and documentation. This reduces duplication and avoids mismatch between different teams. And it also improves collaboration between hardware verification software teams because everyone is working from the same specification. So input formats play a key role in making SoC development scalable, consistent, and less error prone. So structured input formats help convert specification into consistent design artifacts, are a key enabler of automation in modern SoC design. Now let's talk about Verilog, which is one of the most widely used hardware description language in digital design. Verilog is used to describe the hardware behavior, not software algorithm. When we write Verilog, we are describing how hardware components like registers, combinational logic, and state machines behave with respect to a clock. In SoC design, Verilog is mainly used at the register transfer level or RTL. At this level, we describe how data moves between registers on each clock cycle and how control logic manages that data flow. The one important reason Verilog is so popular is that it provides a good balance between abstraction and hardware accuracy. It allows designers to describe complex hardware system in a readable and structured way while still being close to actual hardware implementation. Some of the key concepts, if I name in Verilog, include modules, which represent hardware blocks, registers and wires, which model storage and connection, always block, always is a keyword, which describes sequential combinational logic, the clocks and resets, which control timing behavior. So Verilog plays a critical role in the design flow. It acts as a bridge between specification and hardware because architectural ideas and functional requirements are eventually translated into Verilog RTL. Once RTL is written in Verilog, it becomes golden reference for functional verification, synthesis, even software development. Any error at this stage can propagate further, which is why clean and well-structured Verilog code is very important. So let's understand this simple Verilog example, which represents very common hardware structure used in SoC. This module describes a register. A register stores data and updates its value on the clock edge. So first we define the inputs and outputs here. CLK is the clock signal. Reset is to initialize the register with some value. EN is an enable signal that controls when the register updates. Data in, this is the input data which is coming from outside, and data out is the stored value which will be displayed as the output. And the always block is triggered on the positive edge of the clock or the reset signal. This tells us that logic inside is sequential logic. So if reset is active, the register is cleared to 0. If reset is not active and enable is high, the register captures the data in on the rising edge of the clock. If enable is low, the register simply holds its previous value. This type of register is a basic building block in SoC design. It is used in control logic, data path, configuration registers, and pipeline stages. Even though this example is simple, larger SoC designs are built using thousands or millions of similar RTL structures. It can hold a logic of interrupt, it can hold a logic of counter, it can hold a logic of alias, of a paged registers, and much more functionality. So modern SoC design rarely starts from scratch. Instead, it is based on IP selection and reuse. An IP block or intellectual property block is a pre-designed and pre-verified functional block that can be reused across multiple designs. Using IPs help reduce development time, cost, and risk. IP is reuse is important because SoCs are becoming increasingly complex. Designing every block from scratch would be impractical. Reusing IPs allows teams to focus on system integration and value-added functionality. In a typical SoC, multiple IPs are integrated together, including processor, memories, and peripherals. These IPs may come from internal team or third-party vendors. So overall, IP-based design improves productivity, reliability, and time to market, which is why it is widely opted in industry. Let's look at the main types of IP commonly used in an SoC. First are processor IPs. These include CPU cores and sometimes specialized processor. The processor acts as the control unit of the SoC and executes software. Next are memory IPs such as SRAM, ROM, cache, and memory controllers. These IPs store instruction and data required by the processor and other blocks. Then we have peripheral IPs. These include interfaces like UART, SPI, I2C, timers, GPIO, general purpose input output, and communication controllers. Peripheral IPs allow the SoC to interact with external devices. Some IPs are custom designed, while others are licensed from third-party vendors. The choice depends on performance requirements, cost, and reuse strategies. Together, these IPs form functional backbone of the SoC. So when multiple IPs are integrated into an SoC, they need a common way to communicate. So this is where standard interfaces come in. Protocols like AXI and APB are widely used on-chip communication standards. They define how data, address, control signals are exchanged between IP blocks. So high performance IPs typically use AXI and low speed peripheral often use APB. These protocols are part of standardized interconnect framework. Using standard interfaces simplifies IP integration, improve compatibility and makes verification easier. Designers do not need to reinvent the communication logic for very SoC. So standard interfaces play a key role in making IP-based SoC design scalable and reliable. If I particularly talk about the AXI bus protocol, which is ARM AMBA based protocol. So ARM is the company um, who- which introduced the AXI protocol. So it stands for Advanced Extensible Interface, and AXI is high performance on-chip bus protocol widely used in modern SoCs. It is part of the AMBA family. Uh, AMBA family of protocol is and mainly used to connect high-speed components. AXI follows a master-slave architecture. Master initiates transactions such as processors or DMA engines, and slave response such as memory controller or accelerators. One important features of AXI is that it supports parallel communication. Separate channels are used for address data control, which allows multiple transactions to happen efficiently. Because of its high throughput and scalability, AXI is commonly used to connect CPUs, memory systems, and high performance IP inside an SoC. So at conceptual level, you can think of AXI as a high-speed highway inside a chip designed for moving large amounts of data quickly. And on the other hand, we have advanced peripheral bus. So it is a simple low power bus protocol. This also falls in the ARM AMBA family. And unlike AXI, APB is not designed for high data throughput. Uh, APB is mainly used to connect the low speed peripherals such as UARTs, timers, GPIO, and other registers. And in most SoCs, APB peripherals are not connected directly to the processor, but through a bridge, say AXI to APB bridge, which allows high-speed AXI master to communicate with low APB slave device. And in the beginning, I showed the diagram. I showed the AXI and with the help of a bridge, some peripheral devices are being uh, used. So you can think of APB as a service route, simple, slower, but efficient for control operations. And this table summarizes the difference between AXI and APB. So AXI is where performance matters, while APB is used where simplicity and low power are more important. Both protocols coexist in almost every modern SoC. And today, I'm working with these protocols. So in an SoC, AXI handles high-speed data movements, while APB handles simple control and configuration. And in yesterday's session, we went over the front-end design part of SoC development, which includes the specification, the designing, RTL coding, and functional verification. So in SoC development, front-end design is essentially critical because of large number of IPs and complex interactions between them. So IP selections, standard interfaces, and front-end design together form the foundation of a successful SoC. Now let's move into RTL design for SoC, uh, which is where architecture starts turning into real hardware logic. RTL design is the stage where, as I've discussed before, implement the SoC architecture using various languages such as Verilog and VHDL. Verilog we've already covered. And at this point, the high level blocks defined in architects are converted into detailed clock-based logic. So they serve as the golden reference, and in SoC design, RTL is usually combination of custom logic and integrated IPs all connected together in a structured way. And in this stage, each functional block, such as processor, controller, or custom logic, is implemented in the module. These modules are connected at the top level. Special care is taken for the clock and reset logic since SoCs are often contain multiple clocks and operating modes. The goal here is not optimization, but functional correctness and clarity so that verification becomes easier. And it consists of three important paths. Control logic, usually implement the FSM, finite state machines. Second is data path, which handles what data to be processed, how it moves through the system, and interconnect logic, which connects different IPs and blocks together. This includes bus logic and protocol handling. So in SoCs, interconnect design is especially important because many blocks need to communicate efficiently and correctly. So once RTL is written, the next critical activity is functional verification at the SoC level. SoC verification ensures all integrated blocks work correctly together, not just individually. Verification runs in parallel with RTL development and helps catch any functional bugs early when they're easy to fix. So the most common approach to SoC verification is simulation-based verification. Here, test benches apply different scenarios to the SoC RTL and observe the outputs. For large design, UVM is widely used to build reusable and scalable verification environments. The UVM helps manage complexity of structure, test drivers, monitors, and scoreboards. So functional coverage is used to measure how well the design can be tested. It helps answer the question, have we tested all important scenarios? Verification is often the most time-consuming part of SoC development, you can say. And since there were questions on UVM yesterday, so let me go over that in today's session. So UVM stands for Universal Verification Methodology. UVM is a standard verification methodology used to verify complex digital designs such as IPs and SoC. It is built on system Verilog and provides structured way to create reusable and scalable test benches. The main reason UVM is used is complexity. As designs grow larger, simple directed tests are no longer sufficient. UVM helps manage this complexity by organizing verification components in a systematic way. So UVM is widely adopted across industry, making verification environment more portable and reusable across projects. This is very interesting. You can go into more details after this session if you are interested. But a UVM test bench follows a layered architecture. At the top, we have the test, which controls the overall scenario. The test init instantiates an environment which groups together all verification components. Inside the environment, we have agents. Each agent is responsible for verifying one interface. And agents typically contain a sequencer which generates transactions, a driver which drive the signal to the DUT. DUT is design under test, or you can say your Verilog, which you've already written. This is the DUT, and this is the Verilog which you've already written, and this is the entire UVM environment, which is with the help of interface is coordinating with the DUT to test it. So here the sequencer with the help of the driver and interface is uh, sending values here, and monitor is taking back the value, and the scoreboard here is comparing that the value which was written on this Verilog and the value which is coming back from the system, are they equivalent or not for the testing. In UVM, verification is transaction based, not signal based. So here, my underscore transaction here represents a draw transaction, an abstract packet of data, and my underscore SEQ class generates transaction and sends them to driver through the sequencer. This abstraction makes verification more readable and reusable, especially for complex protocols. And functional coverage helps answer a simple question. Have we tested all important scenarios? Coverage is defined using cover groups and cover points. These track whether different values, modes, combination are being exercised. And functional coverage is especially important in SOC verification where exhaustive testing is not possible. Coverage matrix helps guide verification closure and identify untested cases. One powerful feature of UVM is constrained random verification. So instead of writing fixed tests, UVM generates random stimulus within defined constraint. Constraint ensure that only valid and meaningful scenarios are generated. So this approach helps uncover corner cases bug that is difficult to find using directed test and making verification more robust. So as you can see here, constraint is a keyword. This is the name of the constraint in the language which we've kept. And you can say this is the data of the register and inside is a keyword and value between this range and this range, all the values will be fired on this particular data. Uh, Moving on to integration challenges in SOC design. So first is complexity. As more IPs are added, interactions increases, making the system harder to understand and debug. Second is scalability. Design must support future upgrades, additional features, or new configuration without major rework. Third is verification effort. As the system grows, verifying all possible interactions becomes increasingly difficult and time-consuming. Managing these challenges require careful architecture planning and strong verification strategies. So IP integration is the process of assembling multiple reusable IP blocks, such as processor, memories, and peripheral, into a complete SoC. Each IP is usually predefined, verified individually. During integration, we connect these IPs using standard bus interfaces, assign address ranges, ensure clock reset interrupts are wired correctly. Most SoC level bugs appear at this stage due to mismatched assumption between IPs, which is why integration needs careful validation. So here I have this is the recap where I have taken a very simple example so that you can understand the workflow, how it from specification to SoC integration, how it works. So first here, this is the system RDL language in which you can define an adder map. Adder map you can say is the top IP block, which I name it SoC, which has two IPs under it. This is the top SoC, IP1 and IP2. It has set of registers under it. Okay. Now you give it to some engine, automatic engine of generating. Now nobody will write the Verilog code in industry with their hands. So you should know the language, but nobody writes it. Automation is required. So you feed that specification in system RDL to some engine and then generate its Verilog. So this is the Verilog of the IP1 module, which is generated here, and this is the IP2. It has its own clock, reset, enable, data write register, and this is where the data is stored. And on the clock, positive edge of the clock and negative edge of the reset, uh, um, when enable comes, then the data is written on the register. Similarly, here the same thing is happening. Here the value is getting incremented by one. It is kind of a counter, you can say. So these are the two IPs in my SoC. So you again feed these two Verilogs into another system or another tool, which then connects them together. So this is again a top module of the SoC, and this is the port mapping taking place in Verilog language. Clock, dot clock and bracket clock, so they are connected with each other. with the wire clock. So this is connected here. The clock is connected to clock, reset is connected to the top reset, and enables are connected, and registers are there. And ultimately, you again feed this integrated Verilog into a system, and then such a graph is generated where you this graph shows, say this is your IP1 and this is your IP2, and it is connected to the top also. It has and it is connected amongst itself also. And this is the basic part. Like, I know I've taken a simple example, but graph, just to show you, I have taken a complex graph, but I think you can imagine that one big SoC is there. There are two IPs which are connected. But in the real system, there are thousands of such ports and wires which are going around. So this example shows how high-level specification written system RDL is translated into RTL for individual IPs and then integrated into a top-level SoC. Each IP can be developed and verified independently and later connected together at the system level. This approach improves reuse, scalability, and overall design quality. Moving on to simulation. So simulation is used to verify that the design behaves expected before fabrication. At the IP level, we simulate individual blocks in isolation. At the SoC level, we simulate how all the IPs work together. This helps catch integration issues early, such as incorrect address decoding or data transfer problem. Each simulation greatly reduces debugging effort later in the design flow. And simulation is one of the most important steps in SoC design because it allows us to verify functionality before the chip is manufactured. Using simulation tools, we apply test scenarios to the RTL and observe signal over time in a waveform window like the one shown here. Simulation can be done at the IP level to verify individual blocks, at the SoC level to verify interactions between multiple IPs. Commonly used industry tools include QuestaSim, ModelSim, VCS, Xelium. These tools help designers catch functional bugs, and simulation gives confidence that the design works correctly before moving to physical and implementation integration issues early, and significantly reduces development risk and cost. So until now, we talked about the verification, which is done before silicon. Validation is the process of checking whether the actual chip or system behaves correctly in the real world conditions. So I have covered some validation also here. So because validation typically happens after fabrication using real silicon or prototypes. So the goal is to confirm that the chip works as expected when running real software, real workloads, and interacted with real hardware. So in simple terms, verification asks, did we build the design right? And validation asks, did we build the right design? So validation is critical because some issues only appear when the chip is used in real systems. So the table highlights the difference between verification and validation. Verification is done using simulation test benches before the chip is manufactured, and validation is done on real silicon or prototypes, often using development boards and software. Both are essential. Even a fully verified design can fail validation if system level assumptions are incorrect. And validation can be divided into several types. Functional verification checks the chip behaves correctly when running real application. Performance validation ensures that that the chip meets the speed and throughput targets. Power validation measures actual power consumption under different workloads. Compatibility validation checks whether the SoC works correctly with external devices, software stacks, and operating systems. So these tests help ensure the chip is usable in real products. Talking about validation platforms. So before silicon is available, FPGA prototypes or big emulation systems are there, which are used to validate functionality and software. Once silicon arrives, engineers perform silicon bring up, where the chip is powered on for the first time and basic functionality is tested. Most validation tests are software driven using drivers, firmware, operating systems to exercise the SoC. And obviously, validation comes with unique challenges. Unlike simulation, we have limited visibility into internal signals. Debugging is harder because issues may involve both hardware and software. Hardware software interaction bugs are common and difficult to isolate. Also, validation is expensive and time consuming, so efficient planning is very important. To summarize, plays a that validation plays a critical role in the SoC lifecycle. Verification ensures correctness before fabrication, while validation ensures reliability in real world use. So together, verification and validation provide confidence that SoC is ready for production and deployment. And without proper validation, even a well verified chip can fail in the field. Verification proves correctness in simulation, validation proves correctness in reality. Now let's talk about the C tests, which are widely used during validation. So C tests are software programs written in C that run directly on the processor inside the SoC. Unlike simulation-based tests, these tests execute on real hardware or hardware prototypes. C tests are commonly used during silicon bring up and post silicon validation. They help verify whether this SoC behaves correctly when real instructions are executed on real hardware. So, in simple terms, C tests allow us to test the SoC from the software point of view, which is very close to how the chip will be used in actual products. And C tests are typically used after RTL verification is complete, while UVM and simulation verify the design before fabrication. C tests validate the design in real execution environment. These tests may run on FPGA emulators or actual silicon. C tests do not replace verification, they complement it. They help catch system level issues that are difficult to detect in simulation, especially those involving software and hardware interactions. So C-tests are used to validate multiple aspects of the SoC. They verify whether the processor can execute instructions correctly. They test register access, ensuring the reads and writes behave as expected. They validate peripheral devices such as timers, UARTs, and GPIOs. They also test interrupt exception, memory access patterns. Since C-tests interact with the SoC like real software, they're very effective in uncovering integration and configuration issues. Here I have taken a very simple example of C test. Here the tests write a value to a register using memory mapped address and then reads it back to verify correctness. This type of test is very common during early validation and bring up. If the value does not match the written value, it indicates a problem, possibly in the register logic, bus interface, or address mapping. Even though this test looks simple, it is extremely powerful in catching basic but critical hardware issues. And C tests are very important because they test the SoC the way it will actually be used. They validate real execution path involving the processor, memory, and peripherals. They are much faster than simulation and can run long test scenarios. Most importantly, they help uncover hardware software interaction issues, which are a common source of failures in real products. This makes C-tests a key part of validation and system bring-up. While C-tests are very useful, they also have their own set of limitations. They provide limited visibility into internal signals compared to simulation. Debugging failures can be more difficult, especially when hardware and software interact. C-tests are not exhaustive, they cannot cover all corner cases. Therefore, C-tests are always used together with verification and validation methodology, not as a replacement. To summarize, C-tests play a crucial role in SoC validation. They bridge the gap between hardware and software, validate real execution behavior, and help ensure the SoC works correctly in real systems. So C-tests together with verification and validation provide confidence before a chip moves to the production. And to summarize and key takeaways, I hope now you got a gist of it that how a specification can be written, and then an RTL brings the architecture to life uh, using the Verilog or VHDL. Then the functional verification ensures correctness at the system level, and integration and verification complexity are the biggest challenge in SoC development, but how integration takes place, and towards the end, validation and C-tests. Thank you.
We now move to the question and answer session. Participants are requested to post their questions related to the spec to SoC design process in the chat box. We
We will
will
take a
take a
few
few
questions
questions.
focusing on practical design challenges, verification strategies, and industry workflows.
Ma'am, the first question is, what are accelerators in SoC?
There are a lot of components in SoC. There are a lot of IP. SoC is basically combination of a processor. It can be an ARM processor. It can be an Intel Core. It can be any RISC-V, and it has multiple IPs. So accelerator is kind of one of the IPs, you can say.
Which software tool is best preferred?
Um, there is no such best software tool. Every company is striving hard to make uh, their tool the best one. So at the industry level, there are a lot of factors which needs to be considered. There are customers who are making actual, like, for example, Samsung or the Vivo. Vivo is making its own chip for a mobile phone. So they need a tool. So they will consider, according to their specification, to their budget, they will choose whether which tool in the industry, which company they would like to use. So there's always a competition in the industry, obviously.
Is a chip fabricated to have C tests? And does production means in mass number?
I think you were breaking a bit, but I've read the question in the chat window. Uh, so first, obviously, not mass chips are fabricated at once. If first a prototype or a small chip is first comes into play, and that is validated first, and with the help of C tests, the one in the verification tests, we tested in the UVM language, but now since the physical chip is there, the physical chip will not understand the UVM test. The physical chip will understand the C language. So which can be obviously converted into assembly and then goes into it for the testing. So once the prototype chip is passes all the tests, then only it goes up to the mass production. Very nice question.
Other than PPA, any other reason why SOC is preferred?
So, in the modern world, actually, SoC itself is preferred. It is not like you will have multiple chips and with the help of a bus you are connecting everything. Now, since you can say that a very simple example, the televisions and mobile phones were so big, and now everything transistor level is going down. Now we have LCD, LED TVs, we have very small mobile phones. Everything is going to the micro level. So lot of chip and then connecting them together is not the idea. Having one system on chip, one chip having everything on it, it is it is preferred these days.
Ma'am, could you please throw some light on PCB bring up and boot loading?
Sorry, you were breaking off.
Could you please throw some light on PCB bring up and boot loading? And what is the scope of SOCs like controller and AI chips for startup?
Uh, PCB is something which comes at a very later stage. So you can say, I have not covered PCB, but you can say that the chip on the PCB is something which we have covered in this section. So if you have a PCB board and it will have a chip on it, and that chip, how to design that, how to test that, how to bring that up, is what we have covered in this. So I hope you don't confuse both of them. And obviously, AI chips are getting traction these days. Uh, there are loops in hardware language in system RDL, which I mentioned. You would be glad to know that the simple language system idle which I introduced to you today is actually used to define AI chips in the industry these days. Uh, the help of a lot of for loops, the multiple chain of registers are created, and then AI chips are being manufactured these days. Maybe I'll take another session with you on how about the AI chips itself. It is a very vast topic in itself.
Okay, ma'am. Thank you very much, ma'am, for providing such a detailed explanation of all the questions and for such an insightful and technically rich session. Your structured explanation of the spec to SOC journey provided exceptional clarity. Also, participants are requested to fill out the feedback form that has been shared in the chat box that helps us enhance the quality of future ATAL FTPs.
Thank you so much.
We now move on to welcome our second speaker for the day, Dr. C. Ramachandra.
We are privileged to have Dr. C. Ramachandra, consultant at ISRO and Director Semiconductor at 4C Tron, Bangalore, with us today. Dr. Ramachandra is a renowned authority in semiconductor processing and vacuum deposition technologies, with decades of experience contributing to space grade electronics, thin film coatings, and advanced fabrication techniques.
His work has played a vital role in enabling high reliability semiconductor solutions for space applications, and he continues to guide innovation in next generation fabrication technologies.
He will now deliver session 10 titled Leveraging AI/ML Technologies for VLSI and Chip Design. This session will provide insights into how intelligent algorithms are transforming design automation, optimization, and decision making in modern chip design. The chat box will remain open, followed by a Q&A session. We now invite Dr. C. Ramachandra to take the virtual stage and share his expertise with us.
Thanks for nice introduction. I hope I am audible and also PPT is visible. Is it
Yes, sir,
visible
you're
to all
audible.
of you? And you can
Yes,
see
sir.
the PPT.
Yes, sir.
Okay, very nice. Today we are going to discuss role of AI/ML in semiconductor industry. In fact, it is a most wanted topic today. Any engineering college, the first subject which is going to be filled is by AI/ML. And students and faculty is also curious to know after completing this degree, which are all the opportunities where we can get into this one. So, one of the, at least there are many domains where AML plays a significant role. And one of the domain, one of the industries seeking the support from AML is semiconductor. There are many other domains also. I will quickly go through what are the opportunity, what are the challenges are there in semiconductor industries, and how AML can support and solve the problem. In fact, if you want to appreciate the role of AML and significance, you have to go back 100 years and see what we were, how we were solving the problem. So then only understand the importance and significance of AI. For example, if you go to 100 years, or even today, some deep villages are there. In deep villages, it is mainly forest. The distance between one house to another house used to be a kilometer or so. And people live without any comfort, without any support actually. Their survival is the great challenge actually. Somebody encounters a wild animal like elephant or tiger or king cobra, he has to alert others. That is the best first thing he needs to do so that people can take care of themselves actually. So the communication between two person voice through voice actually, and they have some special signature. If they see elephant, they make a one particular types of voice. If they see king cobra, they make a one particular kind of voice. If they see elephant, they make another one. So some signature based on voice communication, and other people understand, they take appropriate precautions, what they should do in case they encounter elephant or tiger or king cobra. They know it actually. So today you are studying information coding. Today you are studying, signal encryption. All these things were already implemented because whatever the voice they generate, limited people used to understand what it means. That means encryption and description was already there. Only this terminology, they did not use it. This was a century-old situation. Now, even if you see some 50 years back, actually, we have seen many man-to-man signal transmission. In fact, we have seen it when I used to travel from Bangalore to Delhi by train, Karnataka Express, those days. Before starting the train, one person goes and he watches everything and makes sure that there is no other train coming, track, everything is free. There is nobody crossing. Then he will raise the green flag. And by seeing that one, the train stops. So this is signal transmission. So we have lived with this kind of world. Then slowly, when the electronics started developing, my previous talk, I have seen the first transistor was made in 1948, but it took 15 years to integrate only 4 transistors. That we realized the first device, operational amplifier. It has brought phenomenal changes in industrial applications. And one of the product out of the operational amplifier was comparator, which was widely used for on-off controller. And even today, we see that application in some devices. And it had certain limitations and problem. We developed a PID controller. PID stands for proportional, integral, and derivative. But they have limited intelligence in that. Then we started adding more and more intelligence to the controller. So it has become adaptive controller, embedded controller, intelligent controller, and today we call AI-driven controller. So it is a way of adding more and more intelligence. We have been doing better and better jobs. So we quickly see how things are developed actually. The first generation of controller was relay controller. It is also called on-off controller. For example, you want to control temperature of a furnace, say 500 degree, 800 degree. Then what you do, you set a reference temperature. My temperature has to be 800 degree. Then you start pumping power to the heating coil through some driver. If temperature reaches 800 degree, then switch is closed, no more power goes. If temperature reduces to below 800 degree, again switch is turned on. So that means by turning on the switch, making on and off, we try to maintain the temperature. This concept can be utilized for controlling many other parameters. It can be gas flow, it can be temperature, any other parameter. Basically, you have a reference signal, that means set value, then actual measured value. These two are covered. And based on the difference, the driver takes action. This was very simple and easy to implement. And even today, some of the home appliances you can see iron box. So once it is hot, it turns off. You see the red light going off. Geyser in the bathroom. So once it is hot, it will turn off. It is okay. Very simple to implement. It is very simple to design, implement, low cost, but it is power inefficient. For example, I want to set the temperature 800 degree. I set it until 800 degree, it consumes the power. Then when temperature becomes more than 800, it switch off. But if it comes even 799, again it turn off full power. So if we calculate the total power consumed, it is not power efficient actually. This is okay for very small application, home appliance. We are not too much worried about power consumption. But when you go to big industry, it becomes very challenging and constraint factor. Therefore, we cannot use this relay controller everywhere. For example, if you consider steel industry, the cost of the power it consumes is nearly 16%. That means if you buy a steel product, if the cost of steel per kg or whatever the unit is $100, $16 is due to the power it consumes. That is a big amount in steel industry. If you go to the silicon crystal, from which we make the silicon wafer for manufacturing the all devices, it is 22%, very big amount. And certain chemical industry, they consume 40%. That means power is almost like another raw material. See not. Therefore, conservation and reduction of the power is very, very significant in many power sensitive industries. Therefore, relay type controller is not at all suitable. We have to improve ourselves. That is the next evolution we see in the PID controller. In PID controller, as the name suggests, it is proportional, integral, and derivative. What is the difference? Suppose I set the temperature 800 degree, same relay controller and this one. In relay controller, I apply full power until it reaches the 800 degree. Here, power we apply is proportional to the difference between the set temperature and actual temperature. When I start with room temperature, maybe 30 degree. So difference is very high. So it takes full power. And as the temperature increases, I reach 500 degrees, 600, 700 degrees. The power I'm going to apply is lesser, it reduces. It does not wait until the 800 degree. Therefore, it is very optimal in utilizing the power. It considers a lot of thermal flow, all these things. That theory we are not going in detail. But basically, proportional means the amount of power I am going to supply is controlled by difference between the actual temperature and set temperature. The actual temperature and real what we set reference values. Therefore, these two, it makes power utilization in an optimal way. And integral and derivative are additional features where it looks for control the small fluctuation. Suppose you are having some furnace operating at 800 degree. For small second, for 1 or 2 seconds, I inject some gases. There will be sudden fluctuation in the temperature because gas comes from room temperature. For that, again, proportional, it don't need to go to the taking full power. It has to operate with small power. So this is taken care by integral and derivative. So this is a second level of our improvement. And even today, it is one of the standard controller in many industries and big industries. So if you look into the response of a PID controller, I have a reference value. The value can be for temperature, value can be for the gas flow. It is any parameter I can control. And if you look into the output, it increases gradually. There will be slight overshoot that we can minimize by optimizing the PID controller parameter, and ultimately stabilizes to the desired value. This is the typical characteristics. And if we can calculate the power consumed of a PID controller total and to the on-off control, it saves the power significantly. And it is considered as one of the strongest, uh, industry driver. It was running, it is running even today in many of the applications. After that, we started adding intelligence. So we had many things like, adaptive controller, so many things, embedded controller, so many intelligence level we keep on adding. So it has basically it is PID controller, but it has taken many intelligence level. And today, the highest level of intelligence we are adding is through neural network. So where it is required, many occasion, many situation, we have too many inputs, not one or two, thousands of inputs. Like if you go to the nuclear reactor, or if you go to the even defense system, so hundreds and thousands of inputs are there, and their combination, several thousand combination, it is not possible at all for a man to decide which one to be turned on, which one to be turned off. Multiple decision metrics are there, and it has to be minimal or zero human interference. In this kind of things, there is no other choice, only neural network controller is important. So it is kind of a conceptual neural network. So you have thousands of inputs, X1, X2, Xn now, and we assign certain weightage factor because it is not necessary that all inputs play significant role in the output. So we have to assign weightage factor, plus there will be some bias factor, and there is some activation function. Therefore, output I'm going to generate is the activation function, then weightage factor, plus input and the bias. So it generates the output based on this one. Here only thing is the number of input can be several hundred or even thousands, and there are millions of combinations. It is virtually impossible for a man to interfere and take the decision. In fact, we keep on adding intelligence to the machine. You can see we have low-level intelligence machine. Many of you might have used Alexa, Siri, and all. It does certain well-defined function. You can ask some simple question: what is the temperature outside, or what time the particular train is leaving, or particular flight is going on. You can ask some simple question. It has ready. It is built-in intelligence. Then we added more and more intelligence. It has become middle level intelligence. It does some computation and take action by itself. And we have seen super level intelligence in 1999. Developed by IBM. It is called Deep Blue. Some of you might have heard actually. The system has played with world chess champion Garry Kasparov and defeated him. So that means playing chess, that too with grandmaster, that too with world champion, you can imagine how much calculation it requires, and it is defeated. So that has given a lot of confidence to the whole industry that we can make the machine to learn any intelligence much above what man can learn. So this was a historical development actually. Then from this one, we have moved. Now we are in ultra super level intelligence. So man cannot do anything at all. There are situations where only ultra super level intelligence has to take place. That means machine, we make the machine to learn. All decision making is done by system. We don't do zero interference from the human being. That is the situation. Where it is required actually, to understand that one, you have to understand the system response. Probably those who study electronic or electrical, there are two types of system. One is casual system Another is non-casual system. So most of you have seen the casual system. What is the meaning of casual system? You can take some PCB, you can take some circuit. The output of a circuit at any time, say T, it is function of input X at that time, and it is a function of input at some previous time. For example, so it has some memory, it depends on the memory at some T minus. Therefore, output depends only on the input at that time T and previous time T minus. This is called casual system. It does not depend on what input it is going to come in the future. So on the other hand, if you take non-casual system, the present output, that means output at T, it depends not only on the input at time T, it depends on input at T minus previous time. Also, it depends on input which is going to coming in the next time, next later, after maybe microsecond or second or maybe hours. So it depends on the system. That means output depends on present, previous and future signal. Now you may wonder how system knows what input is coming in future. So we cannot measure. So it cannot measure it and calculate, but we need to compute it and provide. That is a non-casual system. Today, AML is very, very much required in this non-casual system. There are many non-casual systems where without AML support, we cannot solve the problem. So I'll give you just few examples. Air defense system, spacecraft launching system, any petrochemical industry, nuclear reactor. You have seen recently a small war between India and Pakistan. What happened? The Indian air defense system has proved much, much stronger than enemies actually. It was able to destroy the missile launched by Pakistan. But we have to look into this, how it happens actually. Moment a missile is launched by Pakistan, it is captured by our system, Air India defense system. There are thousands and thousands parameters it has to capture per millisecond. Exact location it is launched, what velocity it is launching, what is the direction it is going, what is the curvature it is taking. It has to calculate. Then our anti-missile system has to be programmed and it should go and hit there and make it to fall on the Pakistan ground. And this has happened. All of you have seen it actually. Here, millions and millions of signals are there. So it's not only past inputs, present input, it has to calculate and feed the future input. Where in next second, where their enemy's missile will be there, which path it is going to come. It has to calculate and feed it actually. This is non-casual system. And India has successfully demonstrated this one. And you have seen how today war is basically how the role of AML plays in this kind of war. It is just impossible for a person to calculate and feed and make the system to work. Millions of inputs will be there. Time is very less. Within microsecond, you have to calculate, system has to implement, and this is all, artificial intelligence plays very, very role. Same thing in spacecraft launching system, because you launch the rocket actually, so you have no time actually. So you have to monitor thousands and thousands of parameters, the temperature, fuel injection, the velocity with which moving, the momentum it is having, thrust, so many parameters are there. You have to compute and calculate some of the futuristic inputs and feed to the system. It is impossible for a person to take action. It is all automated algorithm. They have to take decision and implement it. Otherwise, it is just impossible. Even in petrochemical industries, you might have seen it actually. There are so many chemical reactors are there actually. So many safety factors has to be considered. It's different chemicals in the form of gases, in the form of the liquids are flowing actually. We have to monitor several thousand parameters, temperature, flow rate, their mixing ratio, so many at hundreds and points. And any point which is likely to be dangerous or going to catch fire, we need to initiate action much before the fire catches. Otherwise, if fire catches, it is almost impossible to, suppress it actually. We lose billions of dollars whole plant actually. So petrochemical industry. Even you talk about nuclear reactor, so much in a nuclear fusion. the temperature goes to the 10 to the power of 8 degree. So it is like just like a sun, temperature is like a sun. Everything will melt and vapor out. How to control actually? There are so many safety factors. We cannot control. It is impossible for a person to look into the data and take action. We'll have a millions of inputs, millions of combination, millions of deviation. So we must make machine to learn and take action. It is impossible for a person to interfere and do it. So these are all some examples. It does not mean it is limited. We can find so many examples. Therefore, there are many non-causal system, very critical, and where machine learning and artificial intelligence plays this one important role. Even spacecraft health monitoring. Today, it is one of the biggest challenge. We have thousands of satellites in space, and some may veer out and come out and start moving on its own. They have 5 kg, 10 kg, 20 kg weight. So now we have to detect actually in which direction they are coming actually. What is the probability it can hit our satellite? If the probability is high, the present satellite has to take some deviation and then again come back to the proper orbit. So this is one of the important projects. ISRO is looking for many people to do work on. Already they are working, but still there are a lot of scope for spacecraft health monitoring. There are so many opportunities where multiple signal has to be detected, monitored, processed, and action has to be taken without human interference. Now we are coming to the role of this one in semiconductor devices. So previously, last time I have shown you there are various types of devices we make. It can be analog devices, it can be digital, it can be mixed signal, RF, microwave, even millimeter wave, and nowadays we are making even optical semiconductor for LED, lasers, etc. There are different. All of them are manufactured in fab. So we'll try to see what are the challenges in the wafer fab, what are all the opportunity for to integrate and support the. So as I said, there are different types of devices. One common thing is all the wafer fab requires clean room, maybe of different level. All the wafer fab requires DI water, which is 18 megaohm. This one wafer fab requires ultra pure chemical. When I say ultra pure chemical, it is semiconductor grade. It means we define it by 7N, 8N, 9N. When we say 7N, what is the meaning? It is 99.99999. That means 9 is followed 7 times totally number. That is the meaning. So typically we need 7N, 8N, 9N purity depending upon different. We use high-end equipments, which equipment cost hundreds of millions of dollars, and testing is very challenging. Today we have devices with 200 pin, 400 pin. So there are so many combination of test vectors, and everything has to be completed in a few seconds. We have packaging, we have failure analysis. These are all the supporting structures in a wafer fab. So AML plays various roles in this one. So we're trying to highlight how AML can be connected or linked to solve the problems. So these are all the elements of a wafer fab. We must have a wafer, we must have a design. We have seen courses on design. What are all the challenges and opportunity? Clean room, DI water, ultra pure chemicals, processing equipment, testing, packaging, reliability testing. These are all various elements we have in a wafer fab. Now, we have seen yesterday class from Dr. Shubham, key steps in design. So it's not only design. Once we do design, we have to do simulation. Then we have to optimize the parameter. Then we have to verify. Then only we send it to the manufacturing. And I don't know, many of you might be knowing, those who are working in design, verification is very time consuming. Typically 50% of the time taken in the design goes to the verification. So that much challenges are there in the design. There are various concerns when you do the design. One is, functional testing. I design the chip. to perform certain function. So it has to do it. Apart from that, it is supposed to meet, there are so many challenges. Clock speed is very important. Does it work with given clock speed? Rise time of a signal, fall time of a signal, propagation delay. It may or may not affect the functionality at that time, but it may affect in some other condition. Signal distortion. So you have an output which is supposed to be rectangular, but it may not be rectangular. How it affects the device performance? Jitter, noise, parasitic effect, transmission line effect. We need to consider so many challenges when we do the design. It is not just the functionality. You may design a microprocessor, you may design a FPGA signal and verify the functionality in verification. It is not enough. We have to make sure that it meets all these requirements and does not create a problem when there are certain changes in the input conditions. Another main challenge, and we definitely requires AML support, is PDK compatibility. What is PDK compatibility? It means process development kit. Unfortunately or fortunately, whatever you call, different wafer fab uses different PDK. Suppose you want to make a chip, you want to make a FPGA, you want to make a microprocessor, you want to make a microcontroller. You have designed everything is okay. Now, foundry, you have to fabricate. Fabrication, you have to go to the foundry. But foundry imposes its own constraints, its own requirement. You have to meet that one. Now, you cannot change that one. Therefore, before design, you have to approach the foundry for fabrication. And some foundry generally allocates certain timing. Okay, this month is okay, we take it. You have to completely design before that one. You have to pay some money. And these foundry people put their own restrictions for design. That is not confidential. They are not public. It is only confidential between foundry and the design people. They put their own rules. That means you are designing a chip with certain functionality. You go to the different foundry, their requirement or their constraints are different. You go to another foundry, their requirement and constraints will be different. Because even if it is a microprocessor, even if you take a single transistor, you take a voltage regulator, any chip actually, different foundry has a different fabrication. They have their own restriction and they ensure that your circuit will work if and only if you follow my PDK compatibility. They provide various rules, their own. You cannot change it. If you change that, if you cannot meet that one, they are not responsible for functionality of the device. And these rules, these constraints are different for different foundry. And it is one of the biggest challenge, not only for design people, for everybody. We have so many challenges. As I said, design will take anywhere from 6 months to 1 year. Not earlier than that one. And management to be hitting. So now after design, they have to book the foundry before 3 to 6 months, well in advance. So if we say I'm going to complete my design in this month, they have to pay money and book the foundry. But what happens many times, there will be design in the type out from the design team. They encounter so many problems in simulation, verifications, so many. No, foundry does not wait. They cancel the booking because they have so many other jobs. Now, after you complete the design, maybe after 2 months or 3 months, you may have to find another foundry. Now, that foundry PDK compatibility is a big challenge. So, whatever you have put effort for 1 year, now for PDK, you need to again redesign. That is impossible. How to convert that design for new PDK is very big challenge, and it is really a lot of scope for AML to work on that one. This is the challenge for design people together in India. So, foundry compatibility, different fab uses different PDK. How do we convert a given design, which is meant for one fab or one foundry to another foundry? That conversion is a challenge, and it cannot be done manually. We strongly need the support from AML assisted tool to meet these challenges. There is a big opportunity in this domain. If you look into the Indian scenario, it is very great to see that we have more than 200 VLI design center. They are all doing very well. It's not, it is more than 30, 40 years. They have been doing very well. And they have shown a growth of more than 15%. It is very good for any industry standard. Growth is very good. And they are involved in analog, digital, RF, mixed signal, etc. different times. And huge manpower demand. If somebody after engineering, they want to join real estate design team, there are a couple of design centers. In Bangalore itself, there are 18 design training centers. You have to attend the course for 6 months and 90% job is guaranteed because they give a problem from the industry and make you to work in this 6 months. In this 6 month course, it is as good as your 4-year engineering course. So much will be dumped and you are made to work very hard. It is very good. There are many industry who are providing training on this one. But the challenge is there are two areas where we are, lagging. Today, the success rate of the chip is very low. If you go back and see 30 years back, 40 years back, once we design the chip, more than 90% it will work. If a chip fails, design fails, it was a surprise. But today, complexity of the chip is so high. Nobody expects that it will work first time. In fact, if a chip works, it is a surprise. 30 years back, if chip failed, it was a surprise. Today, if chip works, it is a surprise. They know that there will be some complication. And also, most of the chip design, we don't design everything. For example, DSP, we don't design. Certain functional blocks, we don't design. We import that functional blocks and make appropriate connection. So we have not generated enough IP from India. There are few, but not significant compared to other countries. This is one area we are lagging. And DFT. DFT stands for Design for Testing. So as I said, today number of pin has increased. 200, 400, number of input has increased, number of clock has increased, number of output has increased. So many under constraints we have to test, so many combinations. So this test feature has to be implemented while designing. That is called design for testing. If you have not designed, then it becomes very difficult. So some companies have started, but still it is not good enough. And another is lack of design debug capabilities. As I said, actually, today failure rate is more. It is accepted. But how quickly we solve this problem? Time is the money. That debug capability is not there. That is where I worked earlier in detail. I will just quickly go through what India need to do in coming decades if we want to have sustain the growth in design centers. That is to have our own design debug capabilities. So this is also called VLSI circuit edit technology. What does it mean? There is some mistake in the design. We have to identify that potential mistake, but chip is already fabricated. How do we have to correct that mistake physically? Then we have to verify and validate this correction, then implement the new correction. And these things should happen very fast. When I say very fast, maybe few days, but not definitely few months. If you look back how we were doing earlier, this was the device flow. We design, then design will go to the mask where the mask is fabricated as per the design. The mask will go to the fab, fab will fabricate, then it will come to the test. If it is successful, it will go to the customer. But as I said, in complex chip, 90% it is failure. It comes to the failure analysis. They try to see what functionality it is not working. Then design team will do a lot of simulation, how to correct it. They do redesign, again send it to the mask. This cycle will take 2 to 3 months. And there is no guarantee second cycle will work. It may require couple of or dozens of repetition. One correction, it may not, problem may not occur. And we cannot waste that much time. Today in industry, time is the money. If you don't release the product in time, we lose the business. So this is where the design debug is playing very significant role. Now here what is happening? After design, we make the mask, then it go to fabrication, we test. Moment we do testing and failure analysis, and we do simulate, we come up with certain hypotheses. So possible that mistakes might have happened, what we guess, we correct in 1 or 2 days using a system called focused ion beam system. This is a very expensive system. Technology is quite complicated. I'm not going in detail, but I'm just telling in a just manner. So physical correction of the mistake happens, and it will happen generally in 1 day or 2 days, not more than that one. Again, we test it. So if the chip works as per the requirement, we tell to the design people, see, your mistake is corrected. This is the correction you have to do it. So whatever it used to take months together, that has been now reduced to 1 or 2 days. This is a facility, this is a capability we are missing, and definitely we need to establish this technology. Otherwise, we cannot sustain the growth in VLSI design, which we have been maintained. So how do we do it actually? So we have to do the design analysis, and we have to find out where the mistake might have happened. Edit plan we have to work out. Then, because we are using focused ion beam, we have to remove the packaging of the IC, inspect in optical microscope, and do functional test before doing any edit, and make sure that that electrical failure signature is there. Then certain layer we have to remove. Then we have to edit those structures using focused ion beam system, and we have to again test this device. Now, if the device works as per the requirement, I know that whatever the correction I have done is good, and I can immediately give to the design team feedback. And this will happen within 1 or 2 days. And there can be more than 4 or 5 edits sometimes. Yes, all of them can be done within few days. So it is time is the money. So circuit redesign after really physical correction. I will show you some example in the next coming slides. So this is called schematic edit. That means one gate was wrongly connected, or one connection was missing, one connection is wrongly connected. So in our experience, last time I have shown, if you take any semiconductor device, there are 3 layers. One is gate level, then memory level, and metal. In our experience, more than 90% of the failure in the design comes at the metallization, wrong connection, either missing connection or wrong connection. 90%. It is very unlikely that a transistor will fail on positive design. Unlikely. I don't say 0%, very unlikely. 90% of the problem is due to the wrong connection, missing connection. Somewhere it is not connected, somewhere it is wrongly connected. Only thing is, we need to study this schematic, we need to identify. It is a huge exercise, of course. It will take a couple of days, and we have to physically correct it and again test the device. If the design problem has gone, functionality problem is gone, then we can implement that design. So this is, though it looks very big, it all happens in a few days. So as I said, sometimes some metal connection is wrong. It should have been not there, but it is there. We have to remove it. Some connection is missing. You have to connect it. So this is called metal edit. There are many names for this one. We call blue edit, metal edit, microsurgery. There are so many names for this one. All have got their own significance. So technically speaking, what I am going to do is either I am removing some metals, cutting, which is all micron and submicron scale, or I'm adding some material again, which is in micron scale. The challenge is we have to go to that precise location and either cut the metal without disturbing other metal, or make the metal without shorting other metal. This is happens in a micron scale. So to implement this one, I need to have a precise tool such as focused ion beam system. So this is called microsurgery. Here you can see I have gone to particular location and cut off submicron disconnector without disturbing other layer, other metal structures. So when you take the IC, when IC comes with some packages, the first step what I need to do is decapsulation. So because I am using ion beam, which is high resolution, high energy for doing this microsurgery. So if package is there, it will not penetrate to the material. Therefore, it is important for me to remove the packaging material so that my IC is exposed to the ion beam. This is the first step I need to do it. So ICs comes with different types of packages. Some of them are plastic, some of them are ceramic. There are different ways for removing these chips. There are different, we are not going to in detail. but after we remove the packaging material, the complete die is exposed actually. So it is very important, this decapping method, because it should not cause damage to the wire bond. It should not cause damage to the metal line or anything, because it uses very, very strong chemicals. We have to make sure that it does not cause any damage. We need to inspect all the wire bonds before doing circuit edit. They are intact. Otherwise, any of the bond is broken or damaged, it is useless to continue further. And we have to ensure that there is no sign of corrosion at the wire bond. This we have to inspect all the pins and every part of the location. So before doing any circuit edit. Once we do this one, actually, this is how the focus ion beam system looks configuration wise. See, it has a IR microscope, it has a navigation software, it is a gas assisted etch. We remove the metal, we remove the oxide, we deposit the metal, all this by gas assisted chemical, and we can precisely go to the particular node or location using laser guided trace. So the resolution is typically 0.16 micron. So that much accuracy I can go in any location of the chip. So once you see there are top of metal layers are there, it is covered with nitride layer, polyimide layer. Either we can remove chemically or we can use ion beam to remove this one. Then we have to penetrate and do the surgery. So this is the one case we did it for Wipro. In fact, this was the case where we have seen that there was a wrong connection. We need to disconnect metal at the metal 2 level. So that coordinate we have seen, we know it actually. Then using the navigation tool, we have gone to that particular location. We have removed the top layer and the second metal is now exposed. You can see white, which is metal. Now we have to cut this metal without disturbing the neighboring metal. That is why use such a high-end tool that is focused. Now the metal is disconnected. After that, we test the device. If the device give the good performance, you give the feedback to the designer. See, this was the wrong connection. You have done it. That is how the technology goes. Again, this is another problem where the link metal was missing it actually. So we expose that structure and we deposit by another conducting element. It's not a metal, but it is somewhat conducting metal element. So then again we test it. This is called metal formation, link formation or link breaking. So this is a microsurgery we have to perform in micron or submicron scale. Unfortunately, there are not much literature. I wrote one book long back. That is the only book available which describes various challenges and scope for doing this one. Somebody can refer to this book actually, if they want to go in detail actually. Now, key infrastructure. I have seen that in semiconductor fab, we have clean rooms, we have DI water, we have ultra pure chemicals, we need to monitor this continuously. And they play a very significant role. When our device fails, we need to record the drift and we have to alert generation. I told you the whole device fabrication takes 2 to 3 months, depending upon the process, depending upon the chip actually. That means today there might be some drift in the cleanliness at a particular location. There might be drift in humidity. There might be drift in the temperature. So we should have record of all these things. We have to record it because we come to know the failure of the wafer at the end, after 2 months, after 3 months. But it has undergone so many drift and deviation. And sometimes we have to alert generation. Oh, there is some significant deviation. It might be responsible. We do not know how it affects. But this data, huge data has to be stored and tracked actually. There are very, very complicated equipments like lithography, etching, thin film deposition, doping, implantation, CMP, RTP. RTP stands for rapid thermal processing. Each equipment, at least there are 200 parameters, at least. So we need to monitor the data. We need to monitor their variation. We put a control chart, upper limit, lower limit, whether it is staying within that limit or is it exceeded for some time the limit. These control charts is very, very important because we need to correlate with the device failure if it all happens after 2 months. Similarly, just for example, if you take a plasma etching system, it is important to know what is the RF power, what is the reflected power, what is the vacuum level, what is the gas flow. There are tens of different gases are used, substrate temperature, how it is fluctuating, particle counts in and around the chamber. When the previous was preventive maintenance was done earlier, this term I can list more than 100. I'm just giving some important parameters. There are each equipment, there are 100 parameters that has to be monitored and their variation has to be noted. And whenever there are some substantial deviation, we have to keep a track. This is where there is a lot of scope for AML to later analyze. That I will see in the coming future examples. But there are a lot of process monitoring tools, dozens of process variable, process variation monitoring, and we should have an alert generation. So this equipment, this process has somewhat deviated significantly. We do not know how it affects, but alert should be there. Later on, when we want to analyze, we look into all these alerts. SPC, every equipment, every process, dozens of processes, every process capabilities, because it is continuously running. What is the variation? What is the drift actually? You might familiar with CK, CPK. How do we characterize the process? How deviation is happening? What is the standard deviation? All these things has to be monitored. And we define control charts. For example, if it is a furnace supposed to work at 1000 degrees. So what is the tolerance? I may give 2 degrees. So is it remaining within 1002 and 998? And how long it remained? When it exceeded slightly. So all these control charts should be ready. And alert generation, we put certain alert data. If temperature exceeded by more than 10 degrees, that has to be recorded for some time, maybe in 1 second. So these are all very important. We have a petabyte data in semiconductor. So this is a very, very important. As I said, device fabrication takes 2 to 3 months, depending upon the plant. There are so many hundreds of processes. Each process, there are at least 10 sub-processes. And every sub-process, we have a process charts, control charts, statistical process control. Everything is there. So in spite of taking, and many equipment undergoes preventive maintenance, so many things. So the best situation in the wafer fab is nearly 80% yield. That is the best situation. But sometimes the yield falls to 60, 40, the percentage. It is alarming because if we do not correct it, actually, we lose heavy money. This is a quite challenge where we use AML tools quickly. Here, time is the money. It is not solving the problem. How quickly we solve the problem, that is the challenge. So to have a feel, actually, number of wafers we produce per day is 2000. Number of dies in a wafer is 1000. That means number of dies we produce is 2 million every day. The cost per die, lower end I am taking $10. If you go to higher end, it is even $1000. So $10. So suppose there is a yield loss of 10%. That means from 80% that has come to the 70%. I am losing 2 lakhs dice. I am losing $2 million per day just for $10. 10% yield loss. Sometimes yield loss goes by 20%, 30%. So $2 million means it's very, very big money. India, if you get that much money, we are very, very happy to set up so many research labs. But it comes just in 1 day. This is the loss wafer fab undergoes in 1 day, unless we fix it. Therefore, in yield engineering, time is the money. How quickly we do it actually. There are different teams. Somebody is looking only SPC charts. Somebody is looking different charts. So many people are working and try to correlate where the failure has happened. Also, we have this is wafer fab calculation. How much time we take to fix the problem? If we take 6 hours to fix the problem, the loss is $1 million. If you take 1 day, it is a $4 million. And if you take 2 days to fix the problem, it is $8 million. So even the average time we take is typically 1 day. That means when some problem comes, it takes average time to fix the problem is 1 day. That means we already lost $4 million. Imagine how much money it is important for us actually. So here AI plays a very, very significant role actually. So we have programs through AI. Here what we do is actually when a wafer fails, there are so many commonality program we have developed. We develop and we verify whether this failure is limited to this particular wafer or the whole lot is showing same signature. Suppose failure, it can be hard failure or even soft. Soft means there is some degradation in the certain characterization like leakage current, still it is functional. Functional failure means we cannot use it. Functional failure. It can be functional failure or some performance degradation. So whether it is due to one single wafer or all the 25 wafer has suffered, that gives a lot of clue for us to study. Then machine commonality. Machine commonality means now, as I said, we need to manufacture 2000 wafers per day. It is not possible by single machine. Some process or batch process, you take diffusion. So we load 25 wafers in diffusion. It does. But when you come to the plasma etching, I load only one. I go to lithography, I go by only one. Therefore, the number of equipments in a wafer fab, it is different for different processes. Batch process, I do 25 at a time. Therefore, I need less number of equipments. Some processes like lithography, implantation, I do wafer by wafer. Therefore, I need multiple equipments. 1 minute. So some of the process we need multiple equipments. Lithography, so we need dozens of scanner actually. Similarly, ion implanter, we need dozens of implanter to have 2000 wafer to process per day. Whereas diffusion furnace, we need less number because it is a batch process. Wet chemical etching, it is a batch process. Like that, we need to calculate each equipment. So we have to see lot commonality, machine commonality. Now, suppose we have a problem for the wafer which has come from one particular lithography, but not from the other lithography it is working. So it will identify problem is with this particular machine, not with other machine. Similarly, operator commonality. It runs 24 hours. It is not possible for a single person to work for 24 hours. Everybody works 8 hours. Then next person come in. Is there any commonality? Is the problem coming with wafers where one operator worked and not with other operator? Material commonality. We use wafers from different vendors. We use chemicals from different vendors. We use like a photoresist from different vendor. Is it any material coming from one particular vendor is creating problem or it is a general? Then SPC chart we study. So is there any deviation in the SP charts? PM activity, very important, like plasma etching system, ion implanter. Regularly, we do PM activity. Sometimes it is not done properly. System parameter is not tuned properly. That equipment may give some trouble. So you need to, I'm just mentioning few. So it is not, it's an endless list. Here, AI assisted, support is very much used and very much required in quick troubleshooting and finding the problem. As I said, time is the money. How quickly we do it. Every 6 hours, we are losing $1 million. That we need to keep it in mind. So how do we do it actually? Parametric analysis. As I said, when a device fails, it can be functional failure or parametric failure. When you say parametric failure, there are various structures are there, transistor, wire, contact, metals, capacitor, diode, resistor, whether these individual components are functioning properly or not. Is there any inherent deviation, inherent the design fault in the transistor? Is there a design fault in my wire? So how do we verify this one? For that, see, if you look into this wafer, as we said, it is circular, but individual die, they are rectangular. So we cannot cover all the space in a circle using rectangle. And between two die, there is a space. Between two dies, you can see between two lines, either horizontal, vertical, there is a space. This is called streets. Typically, it is 200 to 300 micron by 200 by 300 micron. These streets are very, very important in yield engineering. So what we do, we fabricate so many structures on these streets. It can be resistor, can be capacitor, it can be transistor, it can be diode, it can be metals, link, it can be wires. Various structures we fabricate. Why do we fabricate actually? When we have a failure in the wafer, we study these individual structure characteristics. I check characteristics of a diode across the whole wafer. That means if my diode or transistor, it is working well, there is no problem in the structure. Similarly, I check the characteristics, the wire, the resistor, all these things. This is to make sure that there is no inherent problem. For example, in diode, there is the excess leakage current most of the place, or degradation voltage is somewhere reduced, then there is some problem in the diode that is reflected in my function failure. So I need to redesign or reroute or do something for the transistor level. So this is very, very important. And these are all called street actually. And this testing is very, very important in the wafer level. This scribe line generally takes 200 by 200 micron in some wafer, or even 300 micron by 300 micron in some wafer. Now, there are various truss structures we design, so we can evaluate characteristics of diode, transistor, capacitor, resistor. And I told actually there are mainly four circuit elements, whether it is a microprocessor or operational amplifier or voltage regulator. There are only four circuit elements, not more than that one. That is resistor, capacitor, diode, transistor. So if these individual structures are working well, I get a confident. So there is nothing wrong in my basic thing. Then other parameter which affects is gate oxide. Gate oxide is typically 1 or 2 nanometer, even 10, 0.5 nanometer deviation it affects. Similarly, memory cell I need to test. So I fabricate these test structures on this scribe line and verify. That gives me a confidence about my design validation. Then once the wafer fails, actually, we need to understand the root cause of the failure. What exactly has happened? What is causing the deviation? So it has two phases. One is cause of the failure, another is root cause finding. When I say cause of the failure, for example, I have some nickel contamination that is shorting two metal line. So I know that is cause of the failure. Nickel is shorting two metal. But where from that nickel has come? We have not put the nickel. Is it not? It has come from somewhere. That is root cause finding. I have to go and fix it. So there are two stages. One is to find the cause of the failure. Another is to fix it. Further, I must know root cause. So this is the important role of failure analysis. So we use so many tools actually. So if you ask me question why FA, what can go wrong? Everything. Everything can go wrong. I may have the problem in the design itself. I cannot, even though design validation has been done, even though simulation verification is done, not 100% guaranteed. Something might be wrong, either small or big. Manufacturing, definitely high chance. There are 200 steps, 2000 sub steps. Manufacturing, anything can go wrong. Testing. So I said devices failed or deviating some parameter, it is by testing. But what is the guarantee that test vectors I have written is correct? Sometimes my test vector itself is wrong. I get the wrong results. So there is no problem in the device. I need to re-look into the test vectors. So we look into this one, cause and failure actually. There is a single failure and cause is single. It is very one-to-one correlation, no problem. Sometimes single cause, maybe single defect, multiple failure. I see that means once I find out this one removed, all the multiple failures will resolve. But I have single failure, multiple causes, and I have multiple failure, multiple causes. So we have a problem when you have single failure and multiple causes, because I have single failure, I find one cause, Oh, I give a feedback to the sub, so it is solved. But when we do it, actually failure still there because there are some more causes causing same failure, some more defects. So we have to be very careful. Similarly, have multiple failure, multiple causes. So we need to validate, we need to verify until all the problems are solved. So there are, this is just for your overall view, how the FA is done. We have electrical failure analysis. That is very important to know where is the deviation, fault isolation technique, which location of the wafer the problem is there, and physical failure analysis, what exactly is the physical defect that is responsible for that point. So there are so many dedicated instruments. When we say electrical failure analysis, one thing is functional test, whether it is working, doing this one. Sometimes device works functionally, still it fails. That is called voltage corner analysis. It is supposed to work at 15 volts. Suppose I slightly reduce or increase the voltage. Does it work properly at the corner of the voltage? Similarly, temperature supposed to work at 25 degree. If I increase the temperature or reduce the temperature, does it work? Temperature corner analysis, they give a lot of feedback on the possible defects. Timing analysis, I work with certain clock frequency. If I slightly vary how it performs. Test vector analysis. So have I generated proper test vectors and simulate the testing conditions. Failure distribution map, very important. Whether the failure is at one point in the wafer or distributed only at the edges or concentrated only in the center. This gives lot of feedback to me on potential causes. Functional or marginal failure. Whether the failure is overall functional, it is not doing. Functionality is there, but marginal failure. When you say marginal failure, leakage current may be more, breakdown voltage may be less, like that, or delay may be more. These are all marginal failure. So we need to understand this one. The important thing is fault isolation technique, like scanning acoustic microscopy, X-ray radiography. They tell liquid crystal analysis. They tell some location where the problem is there, photon emission microscopy. So these are all non-destructive testing. And there are LIVA, SIVA, TIVA. It stands for light-induced voltage alteration, current-induced voltage alteration, temperature-induced voltage alteration. They help in localizing the fault. So if you consider SAM or radiography, SAM means scanning acoustic microscopy, it is X-ray radiography. So this is a non-destructive. It will tell wire bond is okay or not. It's a problem sometimes may not be in the your chip. It may be in the wire bond, it may be in the delamination, it may be some micro cracks like that. It will show the picture without any decapsulation, without any, it is a non-destructive test. Liquid crystal analysis, it will identify which is the hot area in the whole wafer or the chip. So whichever is hot area, it will point out that area is drawing more current. So we have to use phase transition in liquid crystal. There is abrupt changes in optical properties. It will tell which location of the wafer is hot, and that region we need to analyze in detail. So the resolution is typically 1 square micron. And typically effective level, it is good for 3-level metallization. More than that does not work very effectively. And this is photon emission microscope, is very powerful. So it detects emission parts from failing transistor. If anywhere transistor is degraded or failed, actually on that location we get a emission spot, and sometimes we can use backside using IR infrared microscope. So this is it will easily identify failure like leakage current, high standby current, gate oxide breakdown, CHC, channel hot carrier issues. It is very powerful tool. So this is a figure you can see some greenish part. This will indicate below in this there is some part of the structure is damaged. It does not tell anything more. It tells a location. Once it tells the location, we go back to the layout and see in this location what are the functional blocks, what are the probability that transistor is degraded. Further analysis we have to do. It does not tell anything more than the location. That is why it is called fault isolation technique. Isolation means layout in the location is isolated, further study is required. So it is quick it provides very quick results, but some of the detector requires liquid nitrogen cooling, and sometimes we need to thin the sample. Then we use scanning electron microscope to identify the physical fault. We can see gated solid, how it is melted and damaged actually. We can see how gate is thin due to the defocus in lithography. So we capture all this one and confirm that which process the failure is there. Even you can see how the connection between two metals, that is via, is eroded. It has become, connection has gone bad. Using TM, we can capture. So we tell this feedback to the people. So this is one case very interesting where AI has really helped us a lot. Without AI, it is very difficult to solve this kind of problem. We have started a new device. Actually, whenever into a new device, we fabricate, we do not know what kind of problem comes. We have processed 300 lots. 300 means it's a big number. Each lot contains 25. That means 7,500 wafers are completely manufactured. It took more than 2 months. But in all the way for all the lots, we have seen high leakage current. It was a big shocking for us. 300 lots failed, suffered high leakage current. We have to check so many data. As I said, it is a petabyte, 200 process, 2000 sub process. Each process has a SPC chart. So many data, particle count, the variation in the temperature, variation in the humidity, equipment condition, so many parameters, operator who operated. We could not find any clue, any correlation. And it was a big headache for us actually. How to find? No clue is actually. And we have developed a AI-assisted commonality verification. As I said, we verify the commonality. I said commonality means whether is it a wafer from different vendor, it has used chemical from different vendor that has failed. Like that, whether due to different operator, like that commonality we verify. And interestingly, though 300 lots have gone, some 3 lots from different one, they were not affected by leakage current. That was surprising for us. So we did not bother why 300 lots failed, but we started wondering why these 3 lots worked actually. That means it is a success analysis, not failure. We wanted to get some clue and solve the problem. So why 3 lots were not having leakage current? That was the surprise. Then we studied much in detail. One of the good things in wafer fab, I said it is a petabyte data. Every day it generates. And we have data records for more than 1 year. Even when the wafer is fabricated, given to the customer, they encounter some problem, we can look back. Anything has gone back. That much data backup will be there. We started doing success analysis for these 3 lots. There were no deviation process capability. It was as good as 10 lots. No deviation in particle count because each equipment we are supposed to have a cleanliness. Some of them are class 100, some of them are class 10,000, some of them are class 10, class 1. We monitor. We did not see any particle count. There was no deviation in equipment chart. All the equipments are performing well. So we could not find any clue when we do the analysis for these 3 lots. But finally, we find that in one of the process, one of the sub process, it's not even process. That means out of 2000 sub process, in one of the sub process, it has missed the window. You must understand this terminology. What is the meaning of process window? In semiconductor wafer fab, from once it completes one process, you should go to the next process within some time limit. That is called process window. It is not critical for all. Sometimes there is no requirement, but some process it is critical. But in this process, it has missed by nearly 2 hours 30 minutes. And why it happened is the operator was supposed to load and do it actually. There, the department manager, even for every small good news, they give a whole party. They called everybody for lunch, and they're all Chinese. They are heavy eater. If they go for, they spend hours together. They spend nearly 2 hours for eating and 30 minutes going and coming back. And after 2 or 30 minutes, he loaded. That is process. This is the only deviation we could see. One process window, these 3 lot missed it, and by 2 or 30 minutes. And because of that, there is no leakage current. It was quite interesting and challenging for us. Why this process window is It's not creating the leakage current problem. We could not understand. We could not correlate. We did a lot of studies actually. We could not correlate with any failure or any reason actually. But when we do TM study, TM stands for transmission electron microscope. That is the ultimate tool in microscopy where we can really see almost like an atom. Atom level we can go. We saw ultra thin layer of 2 to 3 nanometer of oxide. Because after the process, it was exposed to the atmosphere. The exposed, ultra thin layer of oxide will be generated. It is true for any wafer, silicon wafer. By even at room temperature, such a thin wafer. Now, we want to understand how this oxide layer is affecting. We have done a lot of device simulation, and we noticed that it is preventing diffusion of the boron from the next layer to the previous layer, and it is minimizing the leakage current. So this was the effort, time we have done using all the AI assisted tools actually. So our solution was very simple. Now we introduced another process, deposit a thin oxide layer. It is very fast and it solves the problem. So earlier we suffered 300 lots. So we just added one small process by this study, deposit thin oxide layer of some, 1 nanometer. It solves the problem. So here, role of AI is very, very important. Identifying commonality across so many parameters. Your program, it will run through, it will scan through millions and millions of data and provide the results. Without that, it is impossible to identify or impossible for anybody to look into this kind of solutions. So there are so many opportunities today for AML. As I said, quick conversion of design for different PDK. This is fortunate or unfortunate. Different fab uses different their own process constraints. They impose this constraint on the design people. And another challenge is we are now going to the nanometer scale and high frequency. The transmission line effect becomes very dominating. So we need a proper model, proper analytical capability to calculate the transmission line effect and how quickly we correlate the deviation in SPC and defect mapping. So these things are not possible without the support of AI tools. So process development kit, people who are in the design, they know it is basically bridge between design and manufacturing. Designer make the circuit, make the layout, everything as to meet the functionality of the device. It has many circuit element. It has certain transistor, it has some functional blocks, amplifier, voltage regulator, some microprocessor, so many functional blocks are there. But these functional blocks are okay from the design point of view. But manufacturing, when you go to the foundry, they impose their own constraints. They will not accept your design. They put, this is the minimum gap between one metal to another metal. This is the minimum width at this level metal. There are so many constraints are there. They don't even disclose unless we pay money. Only after you pay money, they disclose. And designer should make sure that it is manufacturing compatible. Whatever the test they do, it is of no use unless it is compatible for manufacturing. And unfortunately, different foundries have different PDK. Their constraints, their rules are different actually. This will be known to you only when you pay some money and accept the book the foundries. Otherwise, they will not tell it is not available at free of cost. Now, where is the problem? Problem comes. What PDK contains, it has library of building blocks. It has its own device library. It has technology data. And these are all different for different foundries, layers, process constraints, verification check. It's got its own this one. Rule files. It has so many rules that you must follow while designing. Otherwise, they will not do it. Most of the design you are learning in academic institute, it is just for a simulation purpose, not for fabrication. You cannot send it to the foundry because they have got their own rules. They have got their own simulation models. They have got their own standard cell library. It should be compatible to that one. Otherwise, that is why designing for manufacturing is different. Designing for understanding. Now, most of the academic institute, what you are doing is, it is for understanding, it is for practicing, but not for foundry. For designing for foundry, it is a big challenge. Now, what is the problem? You are designing. Typical design time take 12 months. Now, so many people are working. 50% of the time goes in verification. After you design, After you do that one, verification is very important. That itself will take 50% of the time. And you assume that it is going to be verified in maybe another 3 months. You have to book the foundry. For that, you have to book well with money. You have to book 3 to 6 months before. But many times you encounter problem in verification. So you cannot deliver the design. You cannot deliver to the foundry. Delay in design causes cancellation. See, foundries are overbooked actually. They don't care if you don't provide. So because you cancelled, but to look after, you may design, you may complete design after 2 months or 3 months. This foundry is already booked, you have to go for another foundry. The main challenge is PDK is different. PDK means there are various rules, various constraints from this one. Now you have put 1 year effort, but again change it means it is very tough task. So how do we convert the given data from one PDK to another PDK? This is a big challenge where we really need the support of AI tools. So you need to understand these constraints, you need to understand the rules, different rules, and implement the corrections so that conversion happens very fast. Otherwise, we are losing the game. So this is the one challenge AI team need to accept, address, and understand. Then transmission line effect. So when we work with low frequency, it is okay. Nowadays, we are working devices with very high frequency, operating frequency, including megahertz, gigahertz, and all. So at low frequency, the impact of signal coupling is very negligible. So when we go to the higher frequency, and also the space is reducing between two metal lines, coupling effect becomes very dominant. Reflection effect, input impedance mismatching. So these are the things we need to consider. So we may have a single metal between two circuit elements. Low frequency does not matter. But when an operating frequency is several megahertz, gigahertz, signal will not be same at all the points. You have studied in transmission line effect that after 6th standard, you understand transmission line effect. Sometimes we have a two metal lines, then you have to understand what is the meaning of characteristic impedance, whether my circuit is properly terminated with proper characteristic impedance. Otherwise, circuit will whatever the signal you are sending from this to element 1 to it gets reflected back. You want to be accepted. So you have to understand transmission line effect and apply to the device structures which are in the submicron and micron scale. Now we have multi-layer in semiconductor device. Each layer there are parallel lines. It is not only coupling in the plane, how the signal is coupled across the plane. So that is also equally challenging. We need to have a models for S parameter, different and complicated structures we have, signal coupling at the same plane and signal coupling across the plane. These are the things we have to compute and we have to minimize. It is not possible to do it in a simple way. So AI tools becomes very, very important to do. Edge engineering. What is the meaning of edge engineering? As I said, wafer is circular and dies are rectangular. So we have a circular wafer containing 500, 700,000 chips. And at the edges, actually, we cannot fabricate complete die. So that is the waste area that we cannot avoid. So edge engineering means, see, generally the losses at the edge is more compared to the center. There are many reasons because we process the wafer, maybe diffusion furnace, the temperature can be more than 1000 degrees. Sometimes lithography exposes the light. So the distribution, you go to plasma etching, we expose to the plasma. The problem is key fabrication process is lithography, etching, thin film deposition. What the problem happens is there is a non-uniform temperature distribution, non-uniform light exposure in lithography, non-uniform plasma density. You have studied plasma. Anybody has studied? It is impossible to make the plasma uniform. There is an inherent repulsion among the ions. They try to spread themselves. So it's difficult to make plasma uniformity. Non-uniform chemical distribution. You are injecting so many chemicals for either etching or deposition. There is no guarantee that 12-inch wafer they go uniformly. That means per square micron only 100 electrons. We cannot dictate. They travel according to the rules of the physics, not by my rule. I cannot say all 100 goes discipline and deposit there. We cannot control the molecules. The transport of the molecule is guided by the rules of the physics, laws of nature. So we have inherently certain yield loss because of this variation. But there is a scope for minimizing these loss that requires very strong tools from AI. We need to analyze all these losses and see how best I can arrange the temperature distribution, how much I can arrange light exposure, how much plasma distribution, how much chemical distribution, what kind of different distribution will minimize my losses at the edges. This is edge engineering. There are dedicated teams they work on, and they use a lot of AI tools. AI tools really plays a very significant role here actually. Chemical reaction, just an example. If you take any chemical reaction, there are three parameters which affects the etching. One is concentration, one is temperature, one is time. It is a common sense. If you increase the concentration, etch rate increases, but not linearly. Similarly, if you increase the temperature, etch rate increases. Again, there is a limit. If you increase beyond limit, chemical itself can decompose. And time, if you increase more, these are things. So how do we adjust this parameter? Now there is a delta T variation in the temperature. If I increase the temperature, etch rate may increase. But how do we adjust the other parameters so that it compensates? That is the tricky business to optimize the process. So this we call it as a nullifying the deviation, because any parameter you take it, they are fluctuating. Temperature fluctuates, chemical concentration fluctuates. Even if you put say time, 1 minute, 2 minutes, there can be millisecond fluctuation. It is not accurate. It is all control is man-made. So what kind of combination of fluctuation we can allow so that it will minimize the deviation? This is a big challenge in yield loss minimization. And this really requires deep understanding of the process mechanism. So what I'm telling is there is a huge and unlimited scope for the AML to play in the semicon. So design, you take actually, we have a lot of role. Manufacturing, there are 200 process, 2000 sub process. How do we understand? How do we control them? Yield engineering, how quickly we analyze the field and get back to the yield engineering, because time is the money. I told 6 hours delay means $1 million we are losing. So how quickly we can do it, and this requires a strong role from AI and ML. So this is the thing I wanted to drive you. There is a huge opportunity in the semiconductor fab. Now I is open for any questions. I will be glad to answer.
Thank you so much, sir. We now invite the participants to post their questions for Dr. Ramachandra in the chat box. There is one question. It says many analysis can be done through Verilog. Can we do all these with Verilog or system Verilog?
See, Verilog is for design. See, now our challenge is not the design alone, is it not? We have a challenge in testing, we have a challenge in fabrication, we have a challenge in characterization. So our problem is when the chip fails or does not work, design verification, we need to do it actually. But problem is not limited to the design. It can be any domain. Therefore, we have to use all the domain. Process we need to characterize. So device structure we have to characterize, transistor structure, performance we have to characterize whether leakage current is okay or not. So this cannot be done by Verilog. Verilog is limited only to verify the design related issues.
Why wafers are always in circular form? Why not square form?
Very, very good question. If you see how this wafer is manufactured, first we grow the silicon crystal. It has to be crystal. How do we grow the silicon crystal? We made the polysilicon in a quartz crucible. We have to heat it to 1420 degrees, that is melting point. Then we dip a seed crystal, and that seed crystal rotates and pulls. Because of rotation, the whole thing comes like a cylinder. It is a 2 meter and today 12 inch. So it takes couple of days to grow the crystal. Because of rotation and pulling, it takes the circular shape. We cannot make it square, any other shape or triangle. It is a natural. Because of rotation, it takes the cylindrical rod.
How about usage of AI as part of design? Small brief, sir.
The design, I said actually there are a lot of challenges in design actually. Particularly, biggest challenge today we are having is PDK compatibility. So how do you translate a given design from one PDK to another? How quickly you can do it by taking 1 year? Now the problem is PDK has different set of rules. Once the set of rule is changed, what parameter, what spacing you have to change it in your design, that is the one AI has to work out. So it has different foundries have different constraints. How quickly you transform the given, your designers were working, going to work for one foundry. Now different foundry has a different rules, different requirements. How to change that one? That is the whole, the manually doing it will take very lot of time. So you have to use AI for that one. Quick doing is very challenging.
What are opportunities in India as new foundries are established?
See, as we have the data, India is going to have 5 foundries, mainly in Gujarat and surrounding that one actually. So that is a huge opportunity for all semiconductor. Each foundries will have typically 2000 engineers, 2000 engineers plus supporting staffs, technician, administration, those things are different. Working level engineers will be 2000. Some of them trained will be manager, some of them are director. They're technically there will be 2000. There will be technicians, there will be many management supporting team. Data handling is very important. We have dedicated team to manage the speech charts and all. There is a dedicated team. It is a huge opportunity from one fab. So we are expecting 5 fabs to come, some in Gujarat, some in Assam and all, but it will take honestly 4 to 5 years. Even if one wafer fab cost $5 billion, if even somebody gives me $5 billion, I cannot start tomorrow. It will take 3 to 4 years to set up such a clean room facility, DI water facility, ultra clean room. So many infrastructure has to be set up. It cannot be done in one day. So therefore, having money, 3 years is the minimum time to implement the wafer. Therefore, by the time you complete the degree now, you will be in the right time to enter.
Okay. How difficult it is to pinpoint the fault location physically?
It is a very good challenge, very good question. It is done parallelly. In fact, I have many case studies done, and very recently I worked in ISRO. This project, 2 years project, I developed some technology which is now patented to capture defects which is buried in the gate level. How quickly I demonstrated, we have patented. This itself, I can take one day, but it is very good question, very challenging, and we have so many techniques to do this one. It is difficult to tell in one line actually, but it's a valid question, very challenging, and I worked a lot on these technologies. And recently I completed a project on ISRO to determine, to capture defects which are buried in the semiconductor. Semiconductor will have hundreds of layers. Sometimes defects are captured, buried in the gate level. How do we see? Gate level is not visible. So I developed a technology and we patented. We got very good results in ISRO, and which was correlating with the device breakdown failures. So last 2 years I did in India. Now India, the technology is available, and any foundries also can come and use our technology. It is a patented technology, it is chargeable, but we are happy to provide that service. And I can talk one day if you wish actually on this one. Very interesting and very challenging.
Thank you, sir, for a truly enlightening and forward-looking session. Your insights
Welcome.
into AI ML driven chips were extremely valuable. We're grateful for your presence and for sharing your vast expertise and experience with our participants. Thank you so much, sir.
Thank you. You can always welcome to contact me.
Before we
Thank you
conclude
all.
today's session, we request all participants to kindly fill out the feedback form for session 10, the link for which has been shared in the chat box. Thank you so much, sir. Thank you, everyone.
Leave